Have you ever stopped to think about how the incredibly tiny, precise components inside your smartphone, or maybe a critical medical device, or even, a classic Swiss watch are manufactured? We're not just talking about pinpoint precision here, but churning these parts out by the millions, or even billions of units. Traditional manufacturing methods often seem, well, far too slow, maybe too wasteful, or simply too labor-intensive to meet those kinds of astronomical demands. Today, we're taking a deep dive into a really fascinating and I think often misunderstood piece of manufacturing tech, the Escomatic Lathe. It's a machine that's a pivotal development, really a game changer for high volume production of small parts. But its genius lies in a surprisingly simple, almost inverted design. Our mission is to unpack the secrets of the Escomatic, clearly distinguish it from its well-known cousin, the Swiss-type CNC lathe, and reveal why this one fundamental design difference completely redefines efficiency and cost. We'll explore what makes it uniquely powerful when it's the absolute best choice and the critical industries built on its silent, speedy work. Okay, let's unpack this.
Yeah, and to truly understand the Escomatic, we really have to go back to its origins. It's quite a story. It begins in the intensely demanding Swiss watch industry, where the need to make millions of perfect tiny parts incredibly fast was this constant pressing challenge. This machine was the ingenious answer to that specific high-stakes problem. It was really conceived out of sheer necessity. At its core, an Escomatic lathe is a specialized turning machine where, uniquely, the material it stays stationary while the cutting tools rotate around it. It's fed from a continuous coil of material, not bars, and it's designed for extremely fast, high-volume production of small, high-precision parts. It effectively reverses the traditional turning process you might picture. What's fascinating here is that while it was transformative from the start, its unique principle is still often misunderstood. But once you grasp this core difference, its incredible power for certain jobs becomes crystal clear.
I think you hit on a crucial point there because many people, and I'll include myself, often tend to lump all Swiss type lathes into one general category. But what you're describing sounds like the Escomatic design literally flips the entire conventional turning concept on its head. And assuming they're the same, well, that could lead to costly mistakes in manufacturing planning, right? Choosing the wrong machine. So if it's a Swiss type but fundamentally different, what is the core distinction? What truly sets the Escomatic apart? Here's where it gets really interesting.
You've absolutely hit the nail on the head. The core difference, and it is a profound one, is quite simply what rotates. Let's maybe visualize this for a second. In a standard, conventional Swiss-type lathe, the material itself, typically a long bar stock, it spins rapidly, and it moves axially, feeding through a guide bushing, which is like a fixed support, holding the material right at the cut towards the cutting tools, which are stationary. But in an Escomatic lathe, the material, fed from a continuous coil, stays completely still. It only feeds axially, moves straight forward like pushing a pencil into a sharpener, but the material itself doesn't spin at all. Instead, the small, lightweight tool head spins rapidly around that stationary material. So it's a complete inversion of motion. The part stands still, the tools dance around it. What's the big payoff from that kinematic inversion? Why do that? Exactly. That kinematic inversion is the secret sauce. It's the key to the Escomatic's incredible speed. Because only the small, lightweight tool head is spinning, it has very low inertia. There's just less mass to accelerate and decelerate, so it can reach extremely high RPMs without significant vibration, and crucially, without an effect called stock whip.
Stock whip?
Yeah, stock whip is what happens when you try to spin a long, thin bar of material too fast. It starts to wobble violently like a jump rope, and that severely limits your RPMs and your precision in traditional setups. It's a major constraint.
That stock whip sounds like a complete nightmare for precision, especially when you're dealing with tiny, intricate parts. So is it fair to say that the Escomatic is essentially bypassing a fundamental physical limitation that other lathes constantly have to fight against?
Absolutely. That's a great way to put it. The Escomatic's low inertia system is engineered for pure speed. It inherently avoids that limitation. A conventional Swiss type, on the other hand, is built differently. It's built for extreme rigidity, especially for long, slender parts, precisely because it supports the rotating bar right at the cut with that guide bushing. That's a different goal entirely.
Okay, so different design philosophies for different goals.
Exactly.
Yeah.
You asked for the comparison point, so let's just lay them out clearly. For primary motion, Escomatic has the tool head rotating around the material. Conventional Swiss type has the material rotating and feeding past tools. Simple enough. For material state, Escomatic's material is stationary, only axially fed. Conventional Swiss type's material is rotating and axially feeding, the core advantage. For the Escomatic, it's extreme speed with no stock whip. For the conventional Swiss type, it's that extreme rigidity and precision, especially for complex, long, slender parts. And finally, rotating mass. Escomatic only spins a small, low-inertia tool head. Conventional Swiss type spins the entire, often heavy bar of material.
Wow. So the critical insight here is this low inertia design doesn't just make it faster. It unlocks a fundamentally different approach to high precision, high volume production. It allows for speeds that would simply, well, rip apart traditional bar stock if you tried to spin it that fast. It's a complete reimagining of the turning process.
Precisely. And if we connect this to the bigger picture, this fundamental difference in design philosophy directly dictates what each machine is best at. One machine is engineered for the ultimate turning speed for relatively simple parts. The other prioritizes ultimate geometric flexibility and material support for more intricate components.
Okay, that makes sense. So for any manufacturer listening, choosing the wrong machine for a high volume job, well, that sounds like it could be a huge financial misstep. You could easily end up with a machine that's far too slow for your needs, eating into your output. Or maybe one that's overly complex and expensive for a relatively simple part, which just kills your profit margin. It's like picking the wrong specialized tool from a vast toolbox you need to understand the task precisely to avoid massive inefficiencies. So how do businesses make this critical choice? What factors guide them to the optimal machine for their specific production needs?
Well, that's where the decision matrix really comes into play. And fundamentally, it boils down to a pretty clear trade-off. Pure speed versus the complexity of the part. If you're looking for extremely high volume production runs, we're talking millions, of relatively simple turn parts, you almost certainly choose an Escomatic lathe. That's its sweet spot. But if you need to make more complex parts, maybe with features like milled flats or cross holes, intricate threads, or if you're working with lower to medium volume runs where setup flexibility is key, then you'd opt for a Swiss-type CNC lathe. Its versatility wins out there.
Okay, so it sounds like a very clear choice. In many cases, speed for simple parts, versatility for complex ones. But what about edge cases? Or maybe a hybrid scenario? Have you seen companies try to, I don't know, force a Swiss type into doing super high volume simple parts or vice versa? And what were the consequences?
Oh, all the time. And it's almost always a costly lesson learned, unfortunately. I remember one client specifically, they tried to produce millions and millions of simple brass connector pins on their existing high-end Swiss-type CNC machines. They already had them, right? Their cycle times were, decent. But they just couldn't keep up with the sheer demand. And their cost per part was significantly higher than competitors using Escomatics. The machine was simply overqualified and, frankly, underutilized for that specific simple task. They eventually invested in an Escomatic for those pins, and their productivity just shot through the roof. Night and day difference.
So trying to make one machine do everything isn't always the smartest financial move.
Not usually, no. Let's break down that decision matrix a bit more formally. First quadrant, low complexity, high volume. This is the Escomatic's undisputed home turf. Think parts like those simple connector pins we mentioned, small rivets, basic shafts, anything needed in the millions, maybe even tens of millions. The machine's inherent speed, plus the incredible efficiency of coil stock, which we absolutely need to talk more about, gives it the absolute lowest cost per part in this quadrant. No contest. Second quadrant, high complexity, variable volume. This is where the Swiss-type CNC really shines. Examples here are things like intricate medical bone screws, with multiple threads and mill features, or maybe jobs with smaller batch sizes where quick changeover and programming versatility are really important. The Swiss type's tooling flexibility just makes it the clear winner for these applications.
Got it. Speed versus complexity, high volume versus flexibility.
Exactly. When I'm a consultant with clients, I almost always boil it down to two basic questions. First, what does the part actually look like? How complex is it? And second, how many million do you need? The answer almost always points directly to the right machine for a sound, and importantly, a profitable decision.
That seems pretty clear cut.
Well, mostly. It's worth acknowledging there's a bit of nuance now. Modern CNC Escomatics have gained more capabilities. They can do some secondary operations, maybe add slightly more complex features than the old cam-driven ones. And on the other side, Swiss-type makers have really focused on reducing cycle times, making their machines faster. So the lines are blurring somewhat at the edges,
Okay, so there's some overlap creeping in.
A little, but for most core applications, sticking to that basic framework speed for simple high volume, flexibility for complex variable volume will guide manufacturers effectively. It helps avoid making an expensive, inefficient mistake. The core principles definitely still hold true.
That makes perfect sense for massive production runs. But let me ask this. For a smaller shop, maybe, or a company launching a new product where demand is still unpredictable, would the initial investment in all the coil handling equipment or maybe the commitment to those continuous runs, could that be a hurdle? Are there situations where traditional bar stock still makes more sense just for flexibility?
Absolutely. That's a very practical point and a good question. For a startup or maybe a job shop with highly variable batch sizes and frequent changeovers,
Yeah.
the upfront cost of the specialized coil feeding and straightening equipment needed for an Escomatic, along with maybe commitment to larger coil orders from suppliers, that can indeed be a barrier. In those cases, the flexibility and perhaps lower initial setup costs of a bar-fed Swiss type, even with its inherent limitations for super high volume, might be the more sensible choice. It's about matching the tool to the entire business model, not just the part itself.
Right, the bigger picture.
But for companies already operating at scale, producing millions of a single component year after year, the coil advantage is it's transformative. It changes everything.
Okay, so we've talked about the kinematic inversion, the tool spinning, but it sounds like there's another hidden hero in the Escomatic's efficiency story, how it handles the raw material itself. You mentioned hidden costs. What are some of those costs that manufacturers often overlook when they're not using this kind of advanced material feeding system like coil?
You're absolutely right to call it a hidden hero. It's huge. Beyond the machine's internal mechanics, the material feeding system is a profound factor. It revolutionizes efficiency in Escomatic operations. Relying on traditional bar stocks, especially for mass production, introduces these often overlooked hidden costs. Things like constant bar changes, which means downtime, significant material remnants that are essentially just scrap metal, and a lot more operator attention needed to keep feeding the machine, all of which chip away at overall efficiency and add up very, very quickly. It's like 1,000 small cuts to your profit margin.
Okay, so how does coil fix that?
Using continuous coil stock significantly cuts those costs and dramatically boosts efficiency. It enables truly continuous 204/7 production. Think about that. And with almost zero material waste, which is incredible. It requires less labor for loading, obviously, and it takes up much less warehouse space compared to storing these huge, heavy bundles of straight bar stock. I've walked through shops where the cost savings just from switching to coil were, well, astronomical. The most visible benefit is the remnant pile, or rather the lack of one. A bar-fed lathe leaves a useless, unmachinable remnant, maybe 10, 15 inches long sometimes, from every single bar it processes. Every single one. Yeah, when you're running millions, maybe tens of millions of parts, those remnants add up to literally tons of scrap metal. It's a huge material loss, a huge waste. Coil stock gets rid of this waste almost entirely because you're essentially using the material down to the very, very end of the coil.
That's a massive difference, not just in the direct material cost, but also thinking about environmental impact, right? Less waste generated. And this ties into a concept I've heard you discuss before, lights out manufacturing. Can you explain how coil stock is the key to achieving that ultimate efficiency dream?
Exactly, and you picked up on the perfect segue there. This brings us right to lights out manufacturing. It's the ultimate goal for many high-volume shops. Completely unattended, continuous production. And coil stock is absolutely key to achieving this. It's the enabler of true autonomy for these machines. A single large coil, depending on the part size and material, can hold enough raw material for an entire shift, maybe even a full 24 hours, of non-stop running. The machine simply keeps going and going. You can literally turn off the lights and let it run through the night.
That's incredible, just running by itself.
It is. Now, contrast this with bar feeders. Even the most sophisticated automated bar feeders, they must stop the machine for, say, 1 to 3 minutes every single time they load a new bar. With the very short cycle times, often seen for these small parts, sometimes just a second or two per part, that downtime adds up incredibly quickly.
Yeah, I can see that.
Imagine losing 2 minutes every, say, 15 or 20 minutes of actual production time. Over hours and days, that represents a significant loss of potential production capacity. It really hurts your output. Coil feeding eliminates this interruption completely. It maximizes uptime and allows a single operator to efficiently oversee a whole cell of machines, rather than constantly tending to just 1 or 2 bar feeders. I remember visiting a factory floor late one night, and it was almost completely silent, just this low hum of these Escomatics churning out parts in the dark. It was almost eerie, but incredibly efficient, a real testament to this technology working as intended.
So the benefits seem huge. Can you break down that cost-benefit comparison a bit more directly?
Sure. Let's look at a few key factors. First, material yield. With coil stock, you're looking at very high efficiency, typically around 99% yield. significantly higher than bar stock, where, like we said, up to 10%, maybe even more, can be lost just in those bar remnants. Second, machine uptime. It's maximized with coil stock because of that continuous feed. Compare that to bar stock, which has high uptime, yes, but it's constantly interrupted by bar loading cycles. Third, labor needs. Minimized with coil stock, thanks to those long unattended runs. This means significantly higher labor needs for bar stock operations, as operators are constantly tending the bar feeders, clearing remnants, loading new bundles, and finally, storage space. Coil stock is relatively compact, often stored vertically. Bar bundles require a large, sprawling footprint in your warehouse. Takes up valuable space.
That paints a very clear picture.
It really raises an important question, I think, for any manufacturer. How much efficiency, how much material, and how much labor are shops truly losing if they aren't at least considering continuous coil feeding for the right high-volume applications?
That's a powerful question indeed. And it really puts into perspective how a seemingly simple choice about raw material can have such profound ripple effects across an entire operation. It's easy to overlook these tiny components, isn't it? Because they are so small, often hidden deep inside larger devices. But they are the silent workhorses enabling so much of our modern world. Just think about how many devices you interact with daily that depend on millions of minuscule, flawless parts working perfectly together. This technology is literally everywhere, silently enabling so much of our daily lives. So, beyond its birthplace in Swiss watches, what are the major industries today that have come to rely so heavily on Escomatic lathes for manufacturing their small, intricate components? Where do we see them most?
Oh, it's hard to overstate their impact now. Escomatic lathes are absolutely vital in, I'd say, three main areas: electronics, automotive, and medical industries. What these sectors often have in common is the need for components like connector pins, tiny shafts, small rivets, specific dental posts. Applications where both high precision and extreme volume are paramount. You need both.
Can you give us a few specific high-volume examples within those sectors, something that really highlights the Escomatic's unique contribution?
Absolutely. Let's start with electronics and connectivity. This is just a massive market for Escomatics. Think about it. Every smartphone, every computer, every 5G tower. They're filled with literally billions of tiny connector pins, sockets, and contacts. These parts are often relatively simple in design, geometrically speaking, but they must be produced by the billions with perfect consistency and, critically, at an extremely low cost per piece. The Escomatic lathe is the absolute workhorse that makes this possible, just churning out these components from coils of brass or copper alloy at incredible speeds.
Right, the sheer scale is hard to comprehend.
It really is. Then there's automotive and e-mobility. The traditional automotive industry uses these machines to produce billions of simple shafts, rivets, and pins for things like timing chains, small valves, intricate fuel system components. But crucially, as the industry moves rapidly towards electric vehicles, the demand for high-quality electrical terminal pins and specialized connectors has just exploded. This creates even more work that is perfectly suited for the Escomatic's high-speed capabilities and its precision. They're essential for the EV revolution.
That's fascinating. I hadn't directly connected them to EVs like that.
Yeah, it's a huge growth area. And finally, in the medical and dental sector. Now, while the most complex medical parts, like advanced bone screws or maybe intricate implantable devices, those are typically made on the more flexible Swiss-type CNC lathes because of their geometric complexity. There is still huge demand for simpler, high-volume components. Escomatic lathes are widely used to produce millions of dental posts, basic pins for surgical instruments, and various high-volume medical disposables. In these cases, consistent quality, ensuring biocompatibility, and achieving a low cost are absolutely key. So you see, the reputation of Escomatic machines, it was born in that exacting Swiss watchmaking world, but their application has successfully spread to basically any sector that needs millions upon millions of identical tiny metal parts. If your business depends on making huge quantities of a relatively simple component perfectly every single time, you are absolutely in the target market for this technology.
So, wrapping this up, what does this all mean for you, the listener? We've seen that Escomatic lathes are these highly specialized workhorses. They offer really unmatched speed for extremely high volume, small part production. And they do it by employing that unique method, rotating the tools around stationary coil stock. This distinctive approach saves immense time, it virtually eliminates material waste, and dramatically drives down the cost per part, but crucially, in the right applications. It's a powerful testament, I think, to how a seemingly subtle engineering inversion, just flipping the motion, can revolutionize an entire industry and touch countless aspects of our daily lives, often without us even knowing it.
Absolutely. And if we connect this back to the bigger picture, it highlights a really crucial principle of innovation, doesn't it? It's not always about adding more complexity or more bells and whistles or layers of technology. Sometimes the most impactful advancements come from elegantly simplifying motion, or, like here, entirely reversing traditional processes. Doing that allows you to achieve previously impossible levels of efficiency, speed, and precision. It's really about challenging the fundamental assumptions of how something should be done.
A different way of thinking.
Exactly. So here's a final thought. Consider all the invisible components in the devices around you right now. Maybe your phone, your car, your smart home gadgets. How many of them owe their very existence, and certainly their affordability, to a machine concept designed over a century ago in the Swiss Alps? A concept that's been constantly refined, sure, but one that literally flipped manufacturing on its head. The next time you hold a sophisticated gadget, just think for a second about the millions of tiny, precise parts hidden inside and the unsung machines that likely churned them out, possibly running through the night, completely unattended, making our modern life possible.